Yeah, okay.
Alternate C, also. Okay, now. Instead of looking at work, I should have been looking towards, but anyhow. So our limit becomes. And everybody got this. We just run through the make sure. We did one very similar last time. F of x plus h, y replace our x with x plus h. We get x plus h squared y plus x plus h y cubed minus f of x y, which is just x squared y plus y cubed x. So it's this. Over h. Okay, well, expanding x plus h squared, we get x squared plus 2h plus h squared, and multiplying that by y, then we get this beautiful thing. And then we get x y cubed plus h y cubed. I don't quite have enough room to write the minus x squared y, which is y cubed x. So that's going to put it here minus x squared y minus y cubed x. All that divided by h. Okay. Now the x squared y matches up with the x squared y, and the y cubed x will match up with the y cubed x and with the big one. Yeah. It's 1 cubed. Okay. So just one. I really don't like the cancellation. I've done a lot of bad cancellations. I'll use color to indicate what's now and what. Okay. So what we're left with in the numerator is 2x8 y plus h squared y plus h y cubed divide that by h. The h's go away. You end up with the limit as h approaches 0 of 2xy plus y cubed plus hy. And if h goes to 0, the hy goes to 0. And you end up with that's y plus y cubed. And that's the same thing we get if we take the derivative of this expression with respect to x. We treat y as a constant, so we just have y times the derivative of x squared, which is 2xy, and there it is. And then we have y cubed x. We take the derivative with respect to x. Y cubed is like a constant, so it's y cubed times the derivative of x, which is 1, so it's y cubed. Okay. And then the partial with respect to y. I'm not going to write these out. Okay, I'm going to write this out. If we take the partial with respect to y, we treat x as a constant. So that we have x squared times the derivative of y with respect to y, which is 1, giving us x squared, and y cubed. Well, the derivative X times the derivative of y cubed, which is X times 3y squared. And if we did the same difference quotient with a y plus h here, just an X, okay? So what we come out with. Okay, so you got this right, you're gonna get that right. That was actually. Looks right here, because you got a y cube, you got these binomial expansion and stuff. But it's no big deal, okay? If you don't know how to do that, and however you do it. Okay, now I want to talk about the whole foundation, chapters 14 and 15, as well as 16, which is this. Okay. Now, some of you, okay, if you look at this edge on, you can see that this edge is pretty straight. And this edge is pretty straight. And this edge is pretty straight. And let's see, this edge here is pretty straight. Look at it. Okay. And I think one of you has one that is like that. Okay. But others have ones that aren't like that. Okay. So actually what we want to do is we want to look at what happens if these edges are straight. All right. And what we want to do is we want to take measurements. Okay. So grab a measuring instrument. Over behind you, over in the corner, there should be some. We short one. Here, a couple of them. Here. It doesn't matter what you measure with, inches or centimeters or whatever, but yeah, millimeter precision is probably a good idea. Okay, so I'm going to measure this and just demonstrate real quickly, because there's some people watching out there, and everybody can do this. And so as soon as everybody's in the classroom, we can make this really specific. But you know, here I'm just measuring this edge. Now I'm looking at the centimeter marks, and I'm getting what, 9.65 centimeters. Let's write that number down. Okay. And then I measure this one over here, and I get 11.1. I'm not really keeping track of which one I'm measuring, but I'm kind of gone from the shortest to the longest. And I can tell which edge is which. I do that, and I'm getting 11.3. Now something's wrong. Okay, well, measurements. I'm going to do this more systematically, but I'm losing track of which edge was which, just to demonstrate that you can do the same thing. Okay, I was intentionally not being very careful. Pretty. Number 3. One page, 11.3 into 9.8, which doesn't gives me a whole lot of confidence. Okay. Now, what I was measuring was the length of the four edges. They're all different. We can also measure. Let's be sure. We think of line as flat. Because there's a flat, right? I caught it, and then I caught it again, and the corner got me on the nerve. So it's okay. My hand will work again someday. I can also measure, okay, if this thing's flat, so I'm measuring the vertical sides. I can also measure the lengths of these upper edges, the hypotenuses of some obvious triangles, and I get one of them is 9. I'm just going to kind of write this down. Now I'm going to ask, is it possible that the top of this thing is flat? There's the numbers. So you can tell if that doesn't move, it's flat or not. 2 out of 3 is not flat. Top of mine appears to be flat. Can we confirm that from these numbers? So think about that for a minute. First of all, I didn't say which side is which. But what could you say about those numbers if one side is flat? What would have to be true if the top is flat? Okay, any ideas? Oh, shoot. You know, recording has been on, although nobody's said anything, so that's good. Okay, so we had a suggestion. Top is flat. If all the 4 corners on the same plane. Of course, plane is a flat thing, and we know how to get equations in planes and so forth. If we know, like, normal vector, well, we get the equation of the plane very easily. I want to review that if you don't know. Okay, well. And the width of this thing, and it's square, the base is square. Not 35, it's 3.5 inches, which is 7. 3.75. I'm going to say that this is 39 or 8.9 by 8.9. Okay. Just arbitrarily, and let's make it easy, as we don't really at this point. A lot of calculations with it. I'm not going to do a lot of things we can actually measure yet. Okay, so let's say that this thing's 9 by 9, right? Okay. Now, it looks like this is the shorter side, so this would be like 8.3 for the shortest vertical edge. It's like 8.3, and then clearly this is going to be the 11 or the 1. Okay. Now the question is 9.6, say, and the 9.8. They're pretty close. Which one is which? This one or the back one? Is this 9.8? Is it 9.6? What about this one? Okay. How do you decide? One way you can decide is really keep track of what order you measure these. Right, I can do that, even though I said I was going. Okay. Mine is flat. Okay, assuming it's flat. And assuming we've got a little bit of uncertainty here. Which one of these goes what? Just seeing if anybody has any ideas before I tell you. Okay, well, you know, somebody said, well, it could be arbitrary. Not really. Because there's only one equation of this plane, if it's a plane. Okay. If it's a plane, then the normal vector, the unit normal is going to be the unit normal, and it's not going to be any different. Well, if I switch these two dimensions, that's going to make this vector lower, let's say, and this vector higher, or vice versa. And the two vectors are not going to be in the same plane. Okay. And there's only one plane that works. Well, what you really want to consider is, okay, if these are in the same plane, what can you say about this vector and this vector in relation to everything else? Okay, I just got a good answer. Said basically that this vector here is going to be parallel to this vector. And of course, this has got to be parallel to this one. Well, that only works out for one choice. Okay, so which choice for my numbers is it? Okay, so we're trying to figure out whether 9.6 goes here or here. Well, the 9.6 goes here. My question is, what's this vector? Now, just run this picture down here on a schematic. And I've put an XYZ coordinate system. Okay. We haven't positioned this on the XYZ coordinate system. We might put this corner of the origins and everything. There's a quadrant. We might decide this one because it's more visible. Right? It doesn't matter. Question is, what's this vector? And it doesn't matter what your coordinate system is, as long as this side's parallel to the y-axis and this side's parallel to the x-axis, you're going to get the same vector. And in this case, the vector is going to be, well, if you have the dimension right here, 9. So that up here, got this triangle with 9 here and 1.3 here. Okay. Got 1.3, which is here and here. Well, that would make this 9J. Plus 1.3K. All right. Well, then what would this number be? Work it out.
And it looks like you already have, because you can made a gesture saying, yeah, it's the same.
So let's look at this back face. Until it's the back face. I've got the purple now. And this is 11.1, which confirms that it's on the back face. And this has to then be the one we haven't used yet, to 9.8. Okay. And then if we do this, we still get a 1.3 here. We see that this vector is also 9J plus 1.3K. So now I know how to label it. Okay. Well, then what's this vector? Is this vector equal to this vector? Work it out. Do the numbers.
Should just take a second.
Okay, well, we confirm then that this vector is -I plus 1.3K. This vector is -9I plus 1.5, right? Now, can you get your unit normal from this?
Well, let's think through how do we get a unit normal here?
Okay, so, after a little hesitation, I'm asking, are we going to get a normal vector? But we want a unit normal. Well, first of all, to get a unit normal, we can get any normal, then pi by its magnitude, right? How do we get a normal vector? That means a vector perpendicular to the plane. Okay. And there's a little hesitation, somebody else, cross product. Yeah. Maybe the first thing you want to think about in a context like this, because to get a vector perpendicular to something, you take two vectors and in that something, you take their cross product. Okay. And since we've got two vectors, okay, this one and this one, we do the cross product. So the normal vector, we'll come back to this in a minute. Okay. And there's no point doing a determiner of this, but you can if you want to waste time. Okay, or if you don't see the distributive law, you're gonna have a 9I and a -9. Well, that's an I cross I. 0. Okay, cross K is 0. So the only things you don't that aren't 0 are the I cross K here and the K cross I here. Okay. Well. Now, what I just said is true. Of course, this vector is 9J plus 3K. Couldn't be that simple because the vector is then going to end up a multiple of J. Normally, that is not in the J direction, right? So I'm still going to use the rule. Because now I have three products that aren't 0. Okay, in the case, so that are going to be 0. Okay, well, J cross I is K. We have a negative there, so we're going to end up with -81 The J cross I is K, J. I don't know what I did, I did J cross K, J cross I is negative K. I got a negative 81 times negative K. That's next. Right, it should be obvious where these are from, and you can calculate cross products with that. Yeah, that's gonna be 13.5 J cross K, that's what I is, so that's. This, and then this is gonna be negative 13.5 K cross I. What's K cross I? K cross I is J, so it's. Negative 13.5 J. Put these in standard order, it's 13.5 I minus 13.5 J plus 81 K. Now let's look at the object, okay? We have got it, it would be in this orientation.
And how are we gonna figure out where the normal vector is?
Well, we're gonna find something that makes a right angle. We should have anticipated this. I can lay flat on that thing. All kinds of things that it's got spot in. This is nothing else. And yeah, this will work. But not for this purpose. Okay. Okay, so now this surface isn't quite flat. It's I can find a little bit so the chalk doesn't fall off unless it sticks to my hand and falls. So I'm gonna kind of prop up this end. We'll do some chalk, so it's more flat. So it's not, you can see a little better. Okay. Now let's see, I can put this on here. Okay, we can see that it's tilted toward the camera. And yeah, something's wrong. I am like, hey, must have done something wrong with the cross product. Because it looks like it has positive component in the X direction, right? Here's vertical. I've got to lean it forward and to the side. Looks like the X and the Y components ought to both be positive. So did I do something wrong with my right hand rule? Was I careless? Or was I just gone? Okay. Now we got the 81K, it has to be up, right? It has to be in this direction and this direction. So both the I and the J should be positive. The I is positive, but I got a negative in the J. How did I get a negative in the J? I did K cross I. Well, K cross I is negative. I'm sorry. Where did I get that? The J cross K is mu and I. And K cross I might have been I cross K. K cross I gives me J. We're getting negative 13.5 there. I don't see where the error is, but there's gotta be one. I don't want to get hung up on it. Just to make sure. That 9J and 1.3 K, the Ks are all positive. Because everything here goes up. This goes up, this goes up. This is a negative 9I, 1.5 K, so there it is. Negative 9I does what it ought to. Because J plus I is negative K, gives me a positive 81 Okay. The way I look at it. K cross I is definitely J. Here's K, here's I, there's J. I think we just discovered that all our models of the universe are incorrect. Because I couldn't have made a mistake. Well. Some mysterious reason. Because of this, it looks like it should be. Oh, wait a minute. Y'all see what I'm doing? Y'all see what I'm screwing up? Okay, forget this. Apparently, it's losing my ability to orient myself in space. Day goes that way, this thing leans this way, it's not good. Okay, I mean, it has to be right. Okay, so now I've reconciled mathematics with the reality. Just by thinking about what I just done. What I had just done, not what I just done, but, okay. So there it is. And now I want to make a unit vector out of it. I just divide by its magnitude. And I'm estimating it's going to be 20, 80, and it's 400. N over magnitude of n. Going to be approximately 13.5 A minus 13.5 J. Plus 81 C over, I'm estimating about 84 or 85. Is that right? Square that, you get about 6,400. Those two go together, give you about 20 square 20, you get 400. That seems right. We got much more. Seems like it's been a little more things. Like I said, it's about 85. Maybe you get something low about 84 and stuff. Anyhow, you do that, then you get the other side. And then you can use that to get the tangent plane. So I'm not going to work out the tangent plane. Now we're normal vector. And we could use this. We don't have to use a unit normal. Unit normal is a little different. And use the point. Okay, now we have to make a decision about where our coordinate system starts. Okay, so I'm going to start our coordinate system here. So that this point is 0, 0 and the x. So this point would be 0, 0, 8.3. So now our x-axis now we have an origin. So this point is now 0, 0, 8.3. This point is 9, 0, 9.6. Yeah. Okay, so now I can put this in function notation in terms of a function of two variables. Okay, that function would be f of 0, 0, 8.3, f of 9, 0, 9.6, f of 9, -9, f of 0, -9, and you can easily see that those would be values. So I could use the point 0, 0, 9. That the equation is plain. Well, actually, I might just go ahead and do that. So our image is we have the point 0, 0, 9. We have a normal vector. I'll just go ahead and use this. I want to go through the calculation. Just focusing right. We have a vector. I'll use abbreviated notation 13.5, -13.5, -1. Then we have a point x, y, z. Okay, and x, y, z. All of the logic of this is on the plane. If the vector x minus 0, y minus 0, z minus 9 dot vector 13.5, 13.5, 81, that should be -13.5 equals 0. However, you're on the plane if this line from this point to x, y, z is perpendicular to normal vector. And then we can easily write that out as 13.5 x times 13.5 y. Plus 81z minus 729 equals 0. There's the equation of your plane. And we can solve this for z. It's going to be 13.5 over 81x minus 13.5 over 81y. I've got my sign on this should be minus, this should be plus, and then it's plus 9. Thank you. Does that work? Yep. Okay. If x is 0 and y is 0, you get z equals 9. Okay. If x is 9 and z is 0, well, x is 9, so you're going to divide 13.5 by 9, and you're going to get 1.5. Well, x is never 9, so I don't know why I would have done that. If x is 9 and y is 0, okay, if x is 9 and y is 0, you get, oh, we get negative. No, x can't be 9. If y is 9 and x is 0, you get 1.5 here. And 1.5 and 9, you get 10.5, and that's not right. Okay, not gonna worry about the details. This is all done right. You get this, and my big point now is. You could then say. F of X, Y equals this. And I think the problem is this 9. That should be 8.3. And it is 008.3. I carelessly put 009. If we replace that 9 by 8.3, this 9 becomes 8.3. And this becomes 8.3 times 81, which is 648 plus 2.4. This number is going to change slightly. Let's see, it's going to be 6.48 and 2.43. I think that might come out 672.3, which is going to change some of these numbers, but it's going to give you the equation of a function that goes through all 4 of these points. And it's a linear function. It's linear in both X and Y. Okay. So this 9 isn't quite right. And the 81 in the denominator isn't quite right. Yeah, the 81 denominator is fine. What it comes out to is do all that. This number comes out 8.3. Now, what's a partial of F with respect to X, and what's a partial of F with respect to Y? So write that one down. Partial of F with respect to X, partial of F with respect to Y. Okay. Okay, there's another problem. It's not always 13.5. Okay, I made a mistake here. I got 13.5 here. 9 times 1.3 is not 13.5. Okay, 9 times 1.3 is 11.7. So the K cross I should have been 11.7, which is going to change this to 11.7, and this. Okay. Wait a minute. Start over here. Negative. Okay. Okay, so partial F with respect to Y is then clearly 11.7 over 81. Okay. But what do we mean by the partial F with respect to X? Couple of things. We mean it's for any point f of x plus h minus f of x divided by h limit. Okay. Well, let this be x and let h be 9. Okay. So f of x plus h is 9.6, right? F of x is 8.3. F of x plus h minus f of x is 1.3. Okay. And divided by h is 9. It's 1.3 over 9. Which is 11.7 over 81. It's wide numerator, but not negative by 9. This is negative 1.5 over 9. This is positive 1.3 over 9. Okay. Well, okay, 1.3 over 9. It's the slope of this line, isn't it? Well, that connects the idea of the derivative with the slope. In this case, it doesn't matter what h is, because it's a straight line. Okay. It's not varying. If you got the plane, then everything is linear. So the slope of this thing is the partial derivative with respect to x, but with respect to y. Okay. And the slope here is the partial derivative with respect to x. But what's the slope of this segment? Well, x is positive in this direction. The segment is decreasing. It's increasing as you go backwards. It's decreasing as you go forwards along the x-axis. So it's a negative slope. There it is. So slope 1.3 over 9 is a partial derivative with respect to x. Okay. So that's the slope. Here. This thing, this whole line. And what's partial derivative with respect to x mean? It means we hold x partial derivative with respect to y. Start throwing things at me. So, okay. Partial derivative with respect to y. It means we hold x constant, which it is along this line, and take derivative with respect to y. Derivative with respect to y, you have a straight line where the plane intersects the YZ plane, the plane of the surface intersects the YZ plane. We get a straight line. Okay. And, well, then the slope here restricted to the YZ plane. The x is holding y constant. Partial derivative with respect to x. Okay. So now you understand a lot about this. You can also see a connection of functions. Okay. We could have started out with just this information. You could have said, okay, you got a plane. Well, first you test to make sure it's really a plane. Make sure all your vectors are parallel with what they ought to be. You know, the vector from here to here has to be parallel to the vector from here to here. So you can develop, get these vectors, take their cross product, you have a normal vector, you pick any of these points, plug in, get the equation of the plane, solve for z, and that's your f of x, y. This right there we have it. Now we have even more. And we don't have huge abundance of time. We've got a little bit of time. Okay. You can find the volume of this thing. How do we find the volume? Well, if it's a flat surface, we just average all four of these points. All four of these altitudes, we get an average altitude. Maybe that works. Okay. We can approximate it with any altitude of any point here. We get something that gives us the volume of the block we would get if we cut it off level at this point. We just cut it here, throw away the top. We've got a lower limit on our volume. Okay. Or we fill it in level with the high point. So we got a rectangle between this height and this height. Okay. So we have a good approximation, a reasonable approximation of a volume, and if we average the two, we might get an accurate result, or at least something that's fairly close. And we can work that out when we study integration in the next chapter. Okay. What I want you to think about is if I have any surface, okay, any surface here, and I approximate it with one of these, approximate the area above a delta x by delta y increment in the plane, then I get pretty good approximation of the volume above that increment. So I partition my region down here in the XY plane. I got a partition X as well as Y. If I partition X, I get a bunch of intervals. If I partition Y, I get a bunch of intervals. And if I put two of the intervals together, I get a little rectangle. Like the bottom of this, base of this stuff, okay? So that comes up, but I want you to kind of keep in mind that this is going to have a lot of applications. Okay, one application is you take one of these, you know that one? Now, this one isn't flat on top. You can see, if you view it along this edge, that there's a curvature. Actually, it's kind of a piecewise linear thing because of the saw I was using. Had a good band saw and conference. I would cut my fingers off and use it. Okay. I've got a band saw. I can't seem to get the blade on it. Okay, anyhow, you got curved sides. Okay. I can say it's simply a smooth curve. I go to this point here. And the slope of this line that's tangent at that point is the partial derivative with respect to y. What's varying here, y, right? X is being held constant. Varying with respect to y. Okay, so I've got a slope here, and that's going to be my partial derivative with respect to y. If I've got a well-behaved function, I can calculate it. And if this actually models the function, then that's going to work. And here I've got a partial derivative with respect to x. Okay, so for a small increment, small region around this point here, plane I get from this partial derivative and this partial derivative is a good approximation of the surface. Now I get away from here and I see that, well, it's not that great an approximation when I get out here. You know, the derivatives all the way down here when I'm over at this point, right? So it's not perfectly linear. If I take a small enough slice of this thing, the derivative is going to stay pretty close to linear. Okay. So I can do a tangent line approximation at this point. I want a tangent line approximation somewhere in here. Well, I just slice it here and slice it here, and then I slice it this way and get a little small sliver and see what the slope is. What's the slope of that sliver in the x direction? What's the slope of that sliver in the y direction? Those are my partial derivatives. Now, if I've got the equation of the function, you see that it's often very easy to calculate the partial derivative. So if we want to go to function we started with, x squared y plus y cubed x. Take the point 2, 3. Okay, x is 2 and y is 3. If x is 2 and y is 3, we get 9 times 6, 27. And we get 27 times 2, 54. That's 81. Okay. 81 to the top. Okay. So this has value of 81. So we know we have the point 2, x is 2, y is 3, and z is 81. Okay. There's a point way up there. And we have a surface. Okay, well, you can kind of conjecture what the surface is. If you hold y constant, it's kind of parabolic here and linear here, and that adds up to some parabolic. And you can ask those questions and visualize them. I have time to write them out. You can do a slice. You can do a slice where x is equal to 2. And now you have some function up here, which locally is kind of parabolic. Okay. And you know where you are in the parabola. You got a slope. What's your partial derivative? What's your partial derivative with respect to x? Well, we're calculating 2xy plus y cubed. If x is 2 and y is 3, that's 2 times 3, 12. And 27 is 39. You have a slope of 39. Slice it this way. Okay. Wait a minute. No, that slice it this way. Slope is 39 at that point. 2, 3, 81. There's your slope. Visualize that. You realize what a slice of that thing would look like. Analogous to the slice we have here. We Steve. And you can ask them what's partial with respect to y. We plug in 2 for x and get 4. Plug in 3 for y, you get 58. So now you know you have a point up there and slope of 39. Anyhow, slope here, slope of 58 this way. Cross product of 2 vectors, both slopes. Just be like I plus 58k, or I plus k plus 58k, I plus 3, okay, whatever. Take the cross product, you get a normal, you got the type. Now you can approximate the value of the function at any point nearby by the value in that time. It's pretty neat stuff. Okay. Now hopefully this will carry you. The next assignment is just on the minutes and continuity. And we have talked about continuity as well. There's only one problem on continuity, but make sure you look at it and understand it. And I think there's another assignment that just introduces partial derivative. And I think we've done that. Okay, so I think you should be well prepared if you think in terms of these figures here and understand what you can. You ought to be in good shape. The next section, first section we'll have for homework next week is on tangent planes. Okay, so we've done most of that. Let me kill the